Question number 1. The movable wire is moved to the right, causing an anticlockwise induced current. The direction of the magnetic induction in the region P points. So we have a frame of paper in which a wire is being moved outwards, and there is a anticlockwise induced current. So there is an anticlockwise induced current, and in this region P, the magnetic induction will be having a direction, and that direction we need to find. So here the motion is in this way, is towards the right, and the current induced is moving in an anticlockwise direction. So surely uh, the magnetic induction, the magnetic field, and the magnetic field which is produced, it will be upwards or it will be downwards. So according to the right hand rule, we have the all the three things are perpendicular to each other, that is the field, the induced current, and the magnetic the magnetic field, the induced current, and the direction all are perpendicular to each other. So here the magnetic induction is coming outwards to up towards the paper. So the correct option is to the right, up the paper, to the left, down into the paper. So it is up the paper. A flux in W2 in a closed circuit of resistance 10 ohms varies with time according to the equation phi equals to 60 square minus 5t plus 1. The magnitude of the induced current at t is equals to 0.25 seconds. What should be? So we need to find the magnitude of the magnetic induced current. So here we have to find the current. Okay, so current is I, which is equals to E upon R, which we need to find. So for that we have given the resistance R but not E. So E will be equals to change in flux with respect to time, and that change in flux is given with an equation that is 6t square minus 5t plus 1. So we'll differentiate this thing with respect to time, and that gives a 12t minus 5, and when t is equals to 0.25, we have the time they have given, t is equals to 0.25 seconds. So we substitute the value of t out here, that is 0.25 minus 5. So overall that comes out to be minus 2 volts. So your E is minus 2 volts now. So if you have E, so we can substitute the value of E out here, and the R, which is about 10 ohms, so that gives you 0.2 amperes of current. So fourth is the correct option. Next sum. A straight conductor of length 0.4 meter is moved with a speed of 7 meters per second perpendicular to the magnetic intensity of 0.9 Tesla. The induced EMF across the conductor is 1.26 volt, 5.04 volt, 2.52 volts, or 25.2 volts. So here we are given the conductor of length. So we have length, which is equals to 0.4 meters. Also we have given speed, that is velocity, that is 0.4 meter, that is 7 meter per second. And then we have the intensity of the magnetic intensity, that is B, which is 0.9 Tesla. So we have to find the induced EMF, that is E, which is equal to BLV. So B is 0.9 multiplied by the length multiplied by the velocity 7. So the overall answer comes to be 2.52 volts, that is E. So your answer is 2.52 volts. Okay, a conductor is moving with a velocity v in a magnetic field, and the induced current is I. If the velocity of the conductor becomes double, the induced current will be 0.5i, 2i, root 2 raised to I, or 4i. So we have a conductor which is moving inside a magnetic field, and the velocity of the conductor is being doubled. So what will be the current inside that conductor will be? So here the EMF induced inside the conductor will be directly proportional to the velocity of the conductor. So if the velocity decreases or doubles, that means the EMF which is being induced, that will also that means the current which is induced, it will also double out. So if the current initially is I, after doubling it becomes 2I. So your correct option is 2I. Okay, if the flux associated with the coil varies at the rate of 1 weber per minute, the induced EMF is 1 volt, 60 volts, 1 upon 60 volts, or 0 volt. So the flux associated with the coil varies at the rate of 1 weber per minute. The induced EMF E is related to the change in flux upon time, and if the change and the flux is changing with respect to time by the rate of 1 Weber per minute, that is 60 seconds, so the voltage will be E, which is equals to 1 upon 60 volt. So second is the correct option. So the next sum. A coil of area 500 centimeters square have 1000 turns is kept perpendicular to a magnetic field of intensity 4 into 10 raised to minus 5 Tesla. If it is rotated by 180 degree in 0.1 seconds, the induced EMF produced is 20 millivolt, 60 millivolts, 40 millivolts, or 80 millivolts. Okay, so we have a coil which is having some area, that is area which is equals to 500 centimeters square, that becomes 500 into 10 raised to minus 4 meters. Okay, so next it is kept perpendicular to the it is having turns n, which is equals to 1000 turns, and kept perpendicular to the magnetic field of intensity, that is B, we have 4 into 10 raised to minus 5 Tesla. And if it is rotated by a certain degree, that is 180 degree, so we have theta 180 degree, and the time t is 0.1 seconds. Okay, so we need to find the induced EMF, where the induced EMF E is equals to d phi by dt, where the flux associated depends on the number of turns, the area, the B, and the angle, which is having 1 minus cos of theta upon the time dt. Okay, so substituting cos to be 180, that gives you the value minus 1, so this becomes 2, 1 plus 1 becomes 2, so this is 2n AB upon dt time t. Okay, so we'll substitute the values now, that is 2 multiplied by n, that is 1000 multiplied by 500 into 10 raised to minus 4 into d, which is 4 into 10 raised to minus 5 upon the time, that is 0.1 seconds. Okay, so going through all the calculations, the answer comes out to be 0.04 volts, that is about 40 millivolt. Okay, so the correct option is 40 millivolts. Okay, a rectangular loop has a sliding connectors PQ of length L and resistance R ohms, and it is moving with a speed V as shown. The setup is placed in a uniform magnetic field going into the plane of paper. The three currents I1, I2 and I3 I1, I2 and IR. So here is the connection, that is P U T S R Q, which is having a battery out here E, which is equals to BLV, and there are three resistance R R R. The current here is I1, the current over here is I2, and the directions are given. So we here, in order to find the total current, in order to find I1, I2 and I, we need to go through the Kirchhoff's voltage law. Okay, so we'll be applying Kirchhoff's voltage law in two loops. One loop is PUTQR and the other loop is RSTQR. Okay, so let's go with the Kirchhoff's voltage law for loop PUTQP. Okay, PUTQP. So we go from P to U, U to T, T to Q, Q to P. So that gives you minus I1R minus IR plus E, that is BLV, which is equals to 0. Okay, next the Kirchhoff's voltage law for loop RSTQR. Okay, RSTQR. So that is, here it should be minus of R. Okay, Ri, okay, minus of Ri, so out here, and then here it will be minus plus of minus of IR2 Ri2 plus BLV, which is equals to 0. So for the two equations we can separate some terms, like the first equation will become we can change the equation to I1 minus Ri1 plus I, sorry, minus plus BLV equals to 0. So that is BLV is equals to R of I1 plus I. Okay, so this is a final equation number 1. and the second equation can be again written as R minus of I plus I2 plus BLV, which is equals to 0. So again BLV equals to R I1 I plus I2, and that is the equation number 2. Now we add both the equations, equation 1 and equation 2. We get this R I1 plus I2. Okay, here we have I1 plus I2 and plus this I, that is 2 times, so that becomes 2I. Okay, and which is equals to BLV plus BLV, that will become 2BLV. Okay, so again, according to the Kirchhoff's current law, we have the total current is equal to that sum of the addition of all the currents, and here there are only two currents, I1 and I2, so I becomes equals to I1 plus I2. So I1 plus I2 will become I plus 2I equals to 2 times BLV. So here the value for I will be equals to, this becomes 3I multiplied by R, which is equals to 2BLV. So I will be equals to 2BLV upon 3R. Okay, also I1 and I2, if we solve, we will get BLV upon 3 times R, and this correct option where I is equals to 2 upon 3 BLV upon R, so that is third one, I1 equals to I2 and I is equals to 2 upon 3 BLV upon R, so that's third one is the correct option. The next question, if n are the numbers of turns in the coil, the value of self-inductance varies as n raised to 0, n raised to 2, n raised to 1 or n raised to minus 2. The value of the self-inductance in a coil varies on the square of the number of the turns of a coil. Okay, so if there are n numbers of turns of coils or turns in a coil, then the self-inductance varies by the square of the number of turns of coil, so that is n square. So third is the right option. If n are the numbers of the turns in a coil, the value of self-inductance varies as n raised to 0, n raised to 2, n raised to 1 or n raised to minus 2. It is n equals to n raised to 2. The self-induction in a plain coil of n turns with the radius r or the length L is given by, the self-inductance L is given by the formula mu naught n square area multiplied by the length, where A is the area of the cross section of the coil, L with the length, and n be the number of turns. So it varies with the square of the number of turns. So self-induction varies with square of the number of turns. So third is the correct option. Pure indicators each of inductance 3H, that's 3 Henry, are connected as shown in the figure. The equivalent inductance between them of the circuit is given as. So here is the circuit where three inductors are connected in such a pattern. So here the connection is there, which shows the first one is connected between the last two, and this second one is connected to the last. So here the connection is such a way that all the three inductors are connected in parallel. So just like resistance are connected in parallel, it gives out the resultant to be 1 ohms. So here when three of them they are connected in parallel, the equivalent inductance comes out to be only 1 Henry. Okay, similar to as the resistance. Okay, what is the self-inductance of a coil which produces 5 volt when the current changes from 3 amps to 2 amps in 1 millisecond? So self-inductance we need to find out, and the formula is L equals to E d change in time upon change in the current, and the current is going from 3 amps to 2 amps, so there is only 1 amp of change in the current. So E is given out to be 5 volts multiplied by the time is 1 millisecond, that means 1 into 10 raised to minus 3 seconds upon the change in the current, that is 1. So entirely the answer becomes 5 into 10 raised to minus 3 millihenry. Okay, so the correct option is fourth, 5 mH. Okay, if n is the number of turns in a circuit coil, then the value of self-inductance varies as n naught n square n raised to minus 2. So if the value of self-inductance, it depends on mu naught n square A and L. A is the area of cross section of the coil, L be the length of the coil, and L be the number of turns of the coil square. So the self induction directly depends on the N square. So in a transformer, the coefficient of mutual inductance is 4 Henry, and if a current of 5 amperes in the primary coil is cut off in 1 upon 1500 second, the EMF at the terminal of the secondary coil will be 10 kilovolt, 15 kilovolt, 30 kilovolts or 60 kilovolts. Okay, so we need to find the EMF that will be at the secondary coil. Okay, so the coefficient of the mutual induction in a transformer will be given by E, which is equals to M di by dt. Okay, so di will be the current, T will be the time, the E will be the voltage, and M will be the mutual induction. So it is given out, mutual induction is given out to be 4 multiplied by the current, which is 5 amperes, upon time, that is 1 upon 15th of a second, that is 1 multiplied by 1500. So the entire thing gives you 4 5s are 20 multiplied by 1500, that is 30 kilovolt. Okay, so the correct option is 230 kilovolts. In a step-up transformer, the output voltage is 2400 volts for 120 volts input. The number of turns of the primary are 75 and the number of turns of the secondary coil are. So we need to find the number of turns in the secondary coil. They are given 150, 1200, 1500 or 1575. Okay, so the formula for the number of turns for in a step-up transformer is N2 is equals to V2 multiplied by N1 upon V1. Okay, so V2 being the voltage and being the output voltage, that is 2400 multiplied by upon V1 will be the input voltage, that is 120 multiplied by N1 be the number of turns of the coil, that is around 75 turns of the primary coil, and N2 will be the secondary coil. So solving all this, you get about 1500 turns in the secondary coil. So 2 is the correct option. Okay, a transformer having efficiency of 90% is working on a 200 volt and 3 kilovolt power supply. If the current in the secondary coil is 6 amps, the voltage across the secondary coil and the conductor in the primary coil respectively are. So we need to find the voltage and the current in the secondary coil. We need to find the voltage in the secondary coil and the current in the primary coil. So first we'll note down the given things, what all are there. So firstly, the efficiency, that is 90%, that gives you 90 upon 100, that is 0.9. Okay, next is working on a 200 volt and 3 kilovolt power supply. So the power which is given is 200 volt of voltage is given, and input power supply is power input is equals to 3 kilovolt. Okay, 3 kilowatt, sorry. And next, if the current in the secondary coil is 6 amps, that is the current in the secondary coil is 6 amps, and the voltage across the secondary coil and the current in the primary coil. So voltage across the secondary coil and current in the primary coil, both of them we need to find. So first we will find the power output, that is the number of turns multiplied by power input, the power output, that depends on the efficiency multiplied by the power input. The efficiency is 0.9 multiplied by the power input is 3 kilowatt, so that gives you 2.7 kilowatt of power output. So here the power is equals to E into I, and for the secondary coil, for power output will be the voltage of the secondary coil multiplied by the current of the secondary coil. So that gives you, we need to find ES. So ES becomes equals to P0 upon IS, where P0 is 2.7 into, that is kilowatt, converted becomes 10 raised to 3 upon IS. IS is 6 amperes, so that gives out to be 450 volts, okay, of voltage across the secondary coil. And next we need to find the current across the primary coil, that is IP. Again we will take the power input, which is equals to the voltage input across the primary coil and the current input across the primary coil, that is equals to IP, which is equals to power input upon EP, that is power input is given as 3 kilovolts, that is 3 into 10 raised to 3 volt, 3 kilowatt, that is 3 into 10 raised to 3 watt upon EP. EP is how much? EP is 200. Okay, so that gives you 15 amps of current. Okay, so it is 15 amps of current and 450 volts of voltage. So 450 15. Third is the correct option. An EMF induced in a rotating coil in a uniform magnetic field is given by. So the EMF induced depends upon E naught sine omega t. Okay, so in a uniform magnetic field it depends on E naught sine omega t. So we have the options E equals to E naught sine omega t, E cos omega t, E naught tan omega t, or E sine omega t. It is E equals to E naught sine omega t. The frequency of AC mains in India is 30 Hz, 60 Hz, 50 Hz and 120 Hz. So the frequency of alternating current mains in India is it is 60 Hz. Okay, so the correct option is 360 Hz. In the instantaneous current in a circuit is given by I equals to 2 cos omega t plus psi amperes plus 5 amperes. The RMS, the root mean square value of the current is 2 amps, 2 root 2 amps, root 2 amps or 0 amps. So we have the current, that is root mean square current value, which is equals to the peak value upon root 2. Okay, so the peak value will be equals to IRMS multiplied by root 2. Okay, and that means it is I root of 2. So the correct option is second, it is root 2 amperes. Okay, the RMS value of an alternating current of 50 Hz frequency is 10 amps. The time taken by the alternating current in reaching from 0 to maximum value and the peak value of current will be, okay, it is 0.202 seconds or 14.14 amps, 0.01 seconds and 7.07 amps, 0.005 seconds and 7.07 amps, 0.005 seconds and 14.14 amps. So let's see the RMS current to the peak value. We need to find the peak value of the current. So I peak value is equals to IRMS multiplied by root 2, where the IRMS current is given to be 10 amps. So 10 multiplied by root 2, that is 10 multiplied by 14, 1.414, that is the value for root 2. So that gives you 14.14 amps. Okay, next we need to find the time taken to reach the maximum value. So time is given as 50 Hertz, the frequency is 50 Hertz and the time is 1 upon 50. Okay, that is about 0.02 seconds, right? And the time taken to reach the peak is t times upon 4, that is 0.02 upon 4, which is equals to 0.005 seconds. Okay, so the current is the time is 0.005 seconds and the current is 14.14. So 0.005 and 14.14, D is the correct option. Okay, the alternating current, a voltage of V equals to 400 sine 500 pi t is applied across the resistance of 0.2 kilo ohms. Okay, the RMS velocity of the current will be equals to, so we need to find the IRMS value of the current. Okay, and the given things are a resistance is given, that is 0.2 kilo ohms, that gives you 200 ohms. Okay, next is uh, we have an equation V equals to 400 sine 500 pi. Okay, that is it is nothing but E equals to E0 sine omega t. So your E0 becomes 400 volts. Okay, next the formula for IRMS will be equals to E0 upon root 2 multiplied by R, where E0 is 400 upon root 2 is 1.414 multiplied by R is 200. Okay, solving this we get the answer 1.114 amps. So 1.114 is, sorry, we get the answer 1.114 amps. So okay, so alternating voltage V equals to 58 sine 100 pi t and is applied, and flow is I, which is equals to 10 sine 100 pi t plus 65. So the phase difference between the current and the voltage is, so we need to find the phase difference between the current and the voltage, that is it is 60 degrees. So phase difference is 60 degree, and in terms of pi we will get it to be 180 upon 3, so that is pi upon 3. So 3 pi upon 3 is the correct option. In a LCR circuit, an alternating current of alternating EMF E and the current I are given by the equation E equals to 100 sine 100 t volts and I equals to 100 sine 100 t plus pi by 3 milliamperes. The average power dissipated in the circuit will be 100 watt, 10 watt, 5 watt or 2.5 watts. Okay, so we need to find the average power. So where the power, first we'll write the equations. E equals to 100 sine 100 t and I is equals to 100 sine 100 t plus pi by 3. So there is a difference of angle of theta of pi by 3, that is 60 degrees, and the power dissipated is given by E RMS multiplied by I RMS into cos of phi. Okay, so E RMS is nothing but E naught upon root 2 and I RMS is nothing but I naught upon root 2. Multiply this cos of phi, that is cos of 60, that gives you half. Okay, so E naught will be again 100 upon root 2 multiplied by I naught will be again 0.1 upon root 2 multiplied by half, which is equals to, entire thing comes out to be 2.5 watt. So fourth 2.5 watt is the correct option. The phase angle between the voltage and the current during the resonance in an LCR circuit is, in an LCR circuit the phase angle between the voltage and the current is 0. Okay, it is now, it does not show any phase difference between them, so the angle between them is 0. An inductor of 0.5 Henry is connected across a 100 volt 50 hertz supply. The reactance of the circuit is 157 ohms, 15.7 ohms, 1.57 or 0.157 ohms. Okay, so we have given the inductor and we need to find the reactance of the circuit, where the reactance X of the circuit is equals to 2 pi FL, where F is the frequency, L is the inductance, and 2 pi. So 2 into 3.14 multiplied by the frequency of 50 hertz multiplied by the inductance of 0.5 Henry. Okay, so that entire thing gives you to be 157 ohms. So the reactance of the in the circuit is 157 ohms. So first is the right answer. Okay, so in the circuit given below, the key is closed at t equals to 0. The current to the battery is, so here according to the options we need to find the connections to at t equals to 0, also at t equals to infinity when the circuit is at t equals to 0, and when the circuit is closed at t equals to infinity. So firstly we need to find the current to the battery. Firstly, when the circuit is open, then at that time the L will act, this L will act as an open circuit, and hence the current will be equals to V upon R2. Okay, so this the resistance will be the second resistance, but at time t equals to infinity the total resistance will be, these two will up in parallel to each other, so parallel will be R1 R2 upon R1 plus R2. Also the current I will be V upon R of 2, R of the entire equation. Okay, R of the entire equation, which becomes V upon R1 plus R2, R1 R2, R1 plus R2 upon R1 R2. Okay, so the correct option out here is at t equals to 0 V upon R2, and at t equals to infinity V R1 plus R2 upon R1 R2. So third is the correct option. In an AC circuit with a phase voltage V and the current I, the power dissipated is VI upon 2, VI upon root 2, VI, or it depends on the phase voltage V and current I. So in an alternating current where we have a voltage and the current, then the power which is dissipated, it always depends upon the phase voltage, and the current. So fourth is the correct option. The current is not constant, then the power consumed in an AC circuit is small if inductance is very high, resistance is very small, inductance is very small, or resistance is very or the resistance is very high. So here the current is not, if in an AC circuit, if the current is not constant, then the power which has been consumed will be small if the resistance which we are using is small. Okay, because it is an AC circuit, it will the polarities keeps on changing here, so the resistance here will be, if the resistance is kept smaller, then the current consumed will be small. A 100 watt 200 volt bulb is connected to a 160 volt supply. The power consumed would be 64 watt, 100 watt, 80 watts, or 125 watt. So we need to find the power consumed by the bulb, and for that first we need to find the resistance, which is equals to V upon I. So squaring it becomes V square upon IV, that is multiplying and dividing both the terms by V. So V square remains as it is, and I into V becomes the power. So again V is the volt, and that is around 200 volts of bulb, a volt of bulb, and 200 square upon the power which is having, the bulb is having is 100 watt. So that gives you about 400 ohms of resistance the bulb is providing. Next is the power consumed by the bulb, which is equals to E into I. So here E we know what is it, it is 160 multiplied by I becomes equals to E upon R. Okay, so that is again 160 upon R. So this is 160 multiplied by 160 upon the resistance R, that is 400. So the answer is 64 watt. Okay, so the power consumed is option number 1, 64 watt. In an AC current, E equals to 220 sin 100 T is the voltage of voltage is applied. If the impedance is 160 ohms and the phase difference between the current and the voltage is 60 degrees, the power consumption is. So here we need to find the power consumption done by this circuit. So power is equals to E into I. Okay, and that is a cos of phi. So here E into I, the I becomes again E upon R, so that is again equals to E square upon R cos of phi. Okay, so E square, we know E, what is E is equals to here 220, because we have the equation E0 sin omega t. So your E naught peak value is 220 ka square upon the resistance which it is providing is 110 upon the resistance it is providing is 110 multiplied by the cos of phi. The phi is given as 60, so cos 60 becomes half, so that is 1 upon 2. Okay, so the equation is 220 multiplied by 220 upon 110 multiplied by 2, so the answer comes out to be 110 ohms. Okay, the impedance in an LCR circuit is given by impedance Z is equals to under root R square plus x of L minus x of C the whole square. Okay, so first is the correct option. In the following circuit as a resonance, at the resonance what will happen? The power factor is 0, the current through AC source is maximum, or the current through a AC source is minimum, or the current through L and R are equal. This it is a series circuit, so, and that is a series resonance circuit. Therefore the current is always maximum at the resonance. So here the current through the AC source is maximum. 2 is the correct option.